Hello, welcome back to MC312 Thermal Fluid Systems 2, the ideal gas relationship lesson. This video's purpose is to build upon the videos 1 and 2 and to recap the key topics covered during those videos and to solve a student note practice problem. Specifically, we're going to solve a ideal gas problem dealing with both constant specific heats and the variable specific heats assumptions. So let's get right into it here. Looking at the problem we're going to solve today, we have oxygen that we're going to assume is an ideal gas. It's compressed in a piston cylinder device from an initial state of 0.8 meters cubed per kilogram and 290 Kelvin to a final state of 0.05 meters cubed per kilogram and 560 Kelvin. We want to determine the entropy change in kilojoules per kilogram Kelvin of the oxygen during this process from state 1 to state 2. And we want to first solve this assuming the constant specific heat and then the variable specific heats. So this should sound familiar to you from video 2, the two types of equations that we derived. But let's do a quick review. So looking at figure 1.16 out of chapter 1 in your book, this shows how your constant specific heat changes over your changes in temperature. Here we have specific heat at constant pressure graphed with its change in temperature in Kelvin. So you can see, depending on your range of temperatures or the type of ideal gas you are using, you may see no change or very little change in your constant specific heat. Especially there no change if you're dealing with helium and argon there at the bottom. It is constant among all temperature ranges. Or if you look at CO2 there at the top, pretty significant change in your specific heat at constant pressure over your range of temperatures. So if you have a small enough temperature range, it's okay or a good assumption to make the constant specific heat assumption. But if you have a large temperature range, you want to use the variable specific heat assumption. Moving on, let's look at the tables that we talked about in video 2. Table 7, we have our ideal gas specific heats of our common gases. And you can see the actual values of your specific heat at constant pressure or constant volume and our specific heat ratio K for your different temperature ranges and your different gases. Next, we have table 8, the ideal gas properties of air only in this table. And you can see, just a reminder, we have our 3 new convenience functions that we introduced in video 2. There in the middle column, we have our S degree at temperature T. And then next we have our relative pressure, P sub R, and our relative volume, V sub R. Remembering relative pressure and relative volume will only be used when you have an isentropic process. Next, we have table 9, the ideal gas property of selected gases other than air. Just a reminder, the units is on a per molar basis. Make sure you do a proper unit conversion if needed. All right, let's then now look at our 312 RDC, just a reminder of where we'll be getting our equations for today. And we are dealing with an ideal gas, so we'll only need equations here from the ideal gas block. And we'll be using both the constant specific heat equations and the variable specific heat equations today. All right, so let's get back to our problem here and let's solve this for using both constant specific heats and variable specific heats. So top left of your screen, I have your knowns, your find, the diagram and data, and our assumptions. So let's start with our analysis here. And we're going to start with part A. We want to solve part A, our change in entropy assuming our constant specific heats. And remember, we have 2 equations that we derived to solve for our change in entropy assuming constant specific heats. We had equation 6.38 and 6.39. Since we're given specific volume in our knowns, let's start with 6.38, as that is derived using specific volumes. So let's write that out. We have our change in entropy, state 2, minus our entropy at state 1, is equal to our specific heat at constant volume times the natural log of our temperature ratio, T2 over T1. Remember, this must be in absolute, and thankfully it was already given to us in the problem in absolutes in Kelvin, so no need to convert. And all that is plus our universal gas constant, R bar, divided by the molecular weight of our gas in our system, times the natural log of our specific volume at state 2, divided by our specific volume at state 1. Okay, so that is our governing equation. And again, that is equation 6.38 from your text. Okay, so we know our temperatures, we know our specific volumes. We can look at the back of our reference manual or our text to find our universal gas constant R bar. We need to look up our molecular weight for O2, and we also need to look up our specific heat at constant volume for this process. The book talks about two different temperatures to look up your specific heat at constant volume or constant pressure for the constant specific heat assumption. You could look it up at your T average, so you add T2 plus T1 divided by 2, and that's where you look up your specific heat. Or you could look up your specific heat at 300 Kelvin. So for today, we're going to look it up at 300 Kelvin. So let's go to table 7 and go to O2. And at 300 Kelvin, our specific heat at constant volume is equal to 0.659 kilojoules per kilogram Kelvin. And then we need to look up our molecular weight for our O2. We're going to go to table 1. And our molecular weight is equal to 32.0 kilograms per kmol. All right, so now we have all the information we need to solve for our change in entropy. So let's move here to the left side of the screen. And solving this, inputting our values, we have change in entropies is equal to our specific heat at constant volume, 0.659 kilojoules per kilogram Kelvin, times the natural log of our temperatures. Temperature at state 2 is 560 Kelvin, divided by the temperature at state 1, 290 Kelvin, plus our universal gas constant R bar, 8.314 kilojoules per kmol Kelvin, divided by our molecular weight, 32 kilograms per kmol of O2, times the natural log of our specific volumes, 0.05 meters cubed per kilogram at state 2, and 0.8 meters cubed per kilogram at state 1. Okay? Now if we plug all these numbers into your calculator, the answer that you will get for our change in entropies is equal to negative 0.287 kilojoules per kilogram Kelvin. And we will double underline and S that. And that finishes up our analysis for part A. And the constant specific heat assumption of what temperature to look it up at, if you want to review that in your text, you can find that on page 1-27, and your book talks about that. All right, now let's move on to part B. Same overall process as part A, except now we're going to be using the equation for change in entropy, assuming variable specific heats. And if you remember from video 2 of this lesson, that is equation 6.37 from your text. So variable specific heat assumption, and our equation is 6.37. So entropy at state 2 minus entropy at state 1 is equal to our S degree at temperature T2. Remembering our S degree at temperature is a convenience function that we introduced in video 2, and you will look that up in table 9 in this case, or table 8 if you're dealing with air. So S degree at temperature T2 minus our S degree at temperature T1 minus our universal gas constant R bar divided by the molecular weight, uppercase M, times the natural log of our pressure ratio, so P2 divided by P1. Okay, so let's look at what we need to look up in our tables or use the ideal gas equation to solve. So first, we can look up our S degree at temperature T for O2 in table 9. So from table 9 for O2, we get a S degree at temperature T2, which was 560 Kelvin. It's equal to 224.146 kilojoules per k-mole Kelvin. Remembering that our values in table 9 are on a per molar basis, so we put our bar above our S degree. And also a note, we'll need to do a unit conversion. So with that unit conversion, we know that our S degree at temperature T is equal to our molar basis S degree at temperature T divided by the molecular weight of our gas that we are working with. Today is O2. So don't forget to do that conversion, and you should be doing the units check during your does the answer make sense portion. Okay, and then our S degree at temperature T1, which was 290 Kelvin, is equal to 204.218 kilojoules per k-mole Kelvin. And if you use the ideal gas law, you can find your ratio of pressures. So I'll give that to you for time's sake. So our P2 over P1 is equal to 30.90. So we'll use that to input into our natural log function. And again, we just get that using the ideal gas equation. Let's substitute and solve. So substituting, we have our change in entropy is equal to our S degree at temperature T, state 2 minus state 1. And all that is divided by our molecular weight of our O2, which we said was 32 kilograms per k-mole. That's minus our universal gas constant, R bar, 8.314 kilojoules per k-mole Kelvin, divided by our molecular weight of O2. All that times the natural log of our pressure ratio, P2 over P1, which we said was 30.9. Okay? And that gives us a final value for our change in entropy equal to negative 0.269 kilojoules per kilogram Kelvin. And that's comparable to our part A value, which was negative 0.287 kilojoules per kilogram Kelvin. Okay, so this is a good comparison to our answer in part A, which was negative 0.287 kilojoules per kilogram Kelvin. So you can see, depending on your range of temperature and the type of ideal gas you are working with, the constant specific heat assumption is valid, and other times you need to use the variable specific heat assumption and appropriate equations from your RDC, and so that would be something that you would work out during your problem-solving process. Okay, to recap, we did a quick overview of a few key concepts from videos 1 and 2 of the ideal gas relationship lesson, and we solved a student no problem dealing with ideal gas to determine the change in entropy from state 1 to state 2 using both the constant specific heats and the variable specific heat assumption. Hope you enjoyed this video. Have a great day.